been I've been working on this ice stuff for a year, and I realized that maybe nobody else in this lab has any idea what's going on here. And so I just wanted to give a brief overview of what this work is and what we're trying to accomplish. Most importantly, how it's already affected and is going to affect the ModelE code that we all use. So what I'm doing is I'm coupling ModelE in a two-way coupling with the dynamic ice sheet model. So just like soil and plants and urban stuff and aerosols, all these other things that are being added to the model, this is ice is my job right now. So basically that involves two-way coupling is two things. We've taken ice sheet model. You take the surface mass balance out of our GCM, out of ModelE, and feed that into the ice sheet model and let the ice sheet kind of grow and ooze around. And then as it changes, as the elevation of the ice sheet changes and its extent changes, you feed that back into ModelE. So like the bottom of the atmosphere might change if the ice goes down or up, or certain areas of land might turn from ice cover to land cover, which affects how they're dealt with inside our GCM, and also obviously affects the albedo. So have real life effects. So here's an example of the kind of thing that a dynamic ice model can do. This is the ISSM model on Antarctica, and what's plotted here is the speed of flow of the ice. And what you can see, so first of all, these are ice shelves here. So all this stuff we're used to seeing now is white on satellite photos, and it is ice, but it's an ice shelf. So this is right here modeling grounded ice. So it looks maybe a little bit different. You see Antarctica has tons of ice shelves around it. And the other thing to notice is that there are these large regions where really not much is going on. See, this black is basically ice velocity of 0. It's very.
This is ice velocity at the top or at the surface? Weighted?
I don't know.
Somewhere.
Somewhere. It's not going to make much of a difference.
But under the flux, it's probably flux.
Yeah. No, it says meters per year here. So it's either at the top.
It could be mass weighted, right?
It's either at the top or it's integrated through. But the way ice flows, it tends to flow kind of very much like a plug-like flow anyway. So, and there are very specific relationships of how the depth and the velocity are related. So, giving you the ice velocity at the top really does tell you a lot. And as you can see, what's happening here is at the top, you have these large diffuse regions where nothing's happening. It's flowing very slowly, and the reasons for that is because the regions are so large, even very slow flow can have a large mass flux. And also, it's very dry, there's very little precipitation there. So, the flow is driven by adding precipitation and adding more snow that kind of weights it down and causes it to flow faster. So areas with more precipitation, you get higher velocities just from that. And then what happens is this ice gets channeled into these fast-moving outlet glaciers. And that's really, in ice studies and ice dynamics, these outlet glaciers is where the action happens. Yes?
Yeah, can I ask, so what would happen if you had no snowfall at all, if you just basically left the ice sheet to itself and you didn't add any mass on top? Would it just kind of spread out under the influence of gravity, or is
Yes,
that too much
that was what I would do.
Okay.
Yeah, so it would still keep spreading out slowly. So basically, ice, you can do your own ice experiments at home. Get a saucer, pour some molasses in it, and watch it kind of sink out under its own weight. Also, we think, we're really impressed by this. Like Antarctica, it's 4,000 meters thick. That's a lot of ice, and it's crushing down and breaking up all the rock and depressing the crust into the mantle and all this crazy stuff. But actually, you know, this ice sheet is, you know, a few thousand kilometers wide. So actually the aspect ratio of thickness to width of the ice sheet is about that of a piece of paper. So, something to think about. So all the action happens at these outlet glaciers, and you know, one thing we become concerned about is that you know, of course we're all worried about, you know, are these ice sheets melting? If so, how fast, and what will that do to sea level rise? And those are some of the big questions. And a lot of that depends on the dynamics of these outlet glaciers. Are they flowing fast? Are they flowing slow? Now we know that a lot of glaciers have dramatically sped up recently. Jakobshavn is a gigantic outlet glacier in Greenland that's, I think, just doubled or tripled in speed in the past few years. What does this mean? You know, obviously, if your outlet is flowing faster, now you're starting to remove ice from the interior of the ice sheet. So my point from a modeling point of view is that these outlet glaciers are really critical, and so, you know, getting them right, I think, can make a huge difference in answers to questions like how long will it take Greenland to melt away? And unfortunately, getting it right also has a lot of challenges. That you really need a very fine resolution here to get the grounding lines in the outlet glaciers. You need a very fine scale mesh, and at the same time you need a very coarse mesh out here where nothing's happening, unless you have infinite compute power. So I'd say the ice sheet models that are going to really solve this problem well need to be multi-scale in that, say, some adaptable meshes and adaptable grid refinement. Another challenge is that a lot of how the outlet glaciers work depends on the basal properties, you know, down below the bedrock. And since we can't see there, we don't really know what's there, and there's this, both the topography and this small-scale topography thing we call the roughness parameter, which is basically, you know, a fudge factor. And, you know, we can try to invert these things, we can send out radar there. And obviously, if we could do a good airplane radar survey of every outlet glacier on the ice sheet, then, you know, we'd have a good chance. But there are 300 of them in Greenland. And no glaciologists I've met have anywhere close to that much funding. So I'd say most of our outlet glaciers are going to be left, you know, unmapped for the most part. Also, sometimes, you know, it's just like rivers of water. You know, rivers can change course from time to time. Well, so can the ice. You know, you can have two glaciers right next to each other that all the ice goes into one and none of it goes into the other. And so one flows fast, the other doesn't. Then at some point that can change. So there are all these challenging complications to understanding how the ice really gets from the middle of the ice sheet out to the outside, and a lot of open questions. At this point, we're leaving those to somebody else, and we're assuming we have an ice sheet model that, you know, something like this that we can use. Any questions at this point? Okay, so yeah, why do we want to do this anyway? Well, we want to address all these important questions, right? What's happening to Greenland? I've heard estimates it'll melt away anywhere from 500 to 5,000 years. So that's not well constrained. You know, how did these ice sheets get started? You know, how did the Laurentide ice sheet grow from nothing at such a low latitude? You know, further in the past, how did the Antarctic ice sheets get there? You know, here's a big one, right? We know that Greenland it's on its way out. I don't think anything's going to save it. But, you know, what about West Antarctica? Well, for a long time people thought, oh, that's just pretty safe, but now they're not so sure. So obviously we want to do sensitivity studies. You know, any serious climate model and climate predictions into the future, we want to know about, you know, as the extent of the ice sheet changes, that changes the albedo of the climate. So how much, you know, how much stock can we put into predictions of the future where we haven't taken that into account? Well, we'll find out. You know, hopefully our answers today are pretty good. So, and obviously paleoclimate, and you know, whatever ice problem you have here, I think hopefully I've convinced you that this is a great, fun, important field, and there will be lots of amazing things we can do if we just have this, you know, sharks with laser beams tied to their heads. Okay, so there are a lot of challenges, of course. So I'd say the first challenge you can see is that, you know, ModelE is low resolution, uses short time steps, and works on a round Earth, as you know. So, but ice models are all high resolution. Right? You saw those outlet glaciers. Some of them are only, in some cases, you need 1 kilometer resolution versus, you know, hundreds of kilometers for our, even our, you know, bestest, fastest, whateverest cube sphere. They work in long time steps. You know, ice is like molasses, only slower. So you don't need this 1 hour, 30-minute type of time steps for the ocean or the atmosphere. It's more like a month. It's your time step. And the other thing that just the way the field is developed, all the ice models out there think the Earth is flat. And the ice dynamic modelers will tell you, well, it's not going to make a difference because the ice sheets are about as thin as a sheet of paper. On the other hand, it is something to be dealt with when you're dealing with coupling it to something that thinks the Earth is round. So another challenge is that you know, you really need to get the precipitation right. So, you know, there are these orographic precipitation models and corrections that, you know, right now we're not using in ModelE that could, you know, maybe distribute it better. So, you know, at the edge of an ice sheet, you have this slope up. So the top of the ice sheet is very high, and you have this slope up over, you know, 60, 100 kilometers getting up there. And so, of course, when the winds come in, orographic precipitation has very specific effects that are well studied. When you send that through ModelE and just give it, you know, the average elevation of this big gigantic grid cell, you'll get a completely different precipitation field. So someday we'll probably want to correct that and get a, you know, we call it downscaling precipitation. It means, you know, figuring out how to move it around so it's correct orographically. I think a lot of open questions there. So another problem is that ice sheet models are high resolution. They want a high resolution surface mass balance. I mean, you know, how much snow fell, how much runoff was there. And, you know, ModelE is low resolution. So we have to find a way to get this low resolution surface mass balance coming out of ModelE and to get a high resolution version for the ice model. Hopefully one that's smooth. I already talked about these outlet glaciers and basal properties. Oh yes, ice shells. So haven't talked about them yet. That, you know, again, that's a big open problem. And, you know, getting the ice shells right in front of the ice sheets is important because we know once you remove ice shelves, the ice behind it starts flowing faster. So it's all coupled, and we don't really know how to model ice shells yet, although there are people working on it. Okay, so I'm going to talk about mostly about this model mismatch challenge, and a little bit about this number 3. I think there are plenty of challenges here. So the resolution mismatch, I promised we're going to talk about height classes. So what that is we have this very coarse GCM grid. We have this very, very fine ice grid. And we're going to define a medium scale grid in between the two. So what we could do, we could compute everything on our very fine ice grid. But now you're starting to involve a lot of extra computation in ModelE that's kind of repetitive. And so we define this medium resolution grid that's coarser than the ice grid and finer than the GCM grid. The way we do that is we take each of our GCM grid cells and we cut it into pieces based on elevation. And so, now we've turned like one GCM grid cell into 3 or 5 or 10, according to the elevation contours. And then, all of the computation we do on our GCM, all the land ice variables, now we do it kind of one per height class. So, we turn one grid cell into 5 or 10. We do this computation 5 or 10 times now instead of once. So, that is more work than just doing it on the GCM grid, but it's a lot less work than doing it hundreds of times over if we use the ice grid. And the key idea here is that different portions of the GCM grid cell, they're at similar elevation, will have similar behavior with respect to an ice model. They're at similar elevation, they should have similar temperature, they should have similar precipitation. So that's why we don't need to consider each ice grid cell individually. We group it into regions of, similar elevation. So here's the idea, right? So this is just, a lat-long grid cell, set of grid cells over Greenland. And here is the elevation of the Greenland ice sheet. And so what we've done, here are these subgrid tiles that we've created by dividing up each GCM grid cell into height classes. So, most of the GCM works on this grid, and now the land ice portion of the GCM keeps tabs of stuff on this grid instead. So you can think of it as funny shaped grid cells. You can think of it as 10 new surface types, surface subtypes inside of land ice. There are many ways you can think of it. I like thinking of it as just, we've defined this grid of funny shaped grid cells, and that's where we do our computation. And so the way they're indexed is if this is grid cell ij, then the corresponding grid cell here is ij1, ij2, and so on, depending on which elevation class it's in. And they're up to 10 elevation classes total, but not every grid cell has to use all 10 of them. So are you interested in talking about how the code has changed, or should we? Okay, so very quickly, we've defined NHC, number of height classes. That's the maximum number of height classes. And that's in the run deck. It defaults to 1. So actually, the main branch of ModelE code is now using this height classified code, and hopefully nobody has noticed. But you can go into your run deck and monkey around and change NHC to something other than 1, and now you'll be running with height classes. FHC, the fraction of each grid cell in each height class. So you need to have some high resolution elevation model and define your height classes. Say height class 1 is between 0 and 100 meter, height class 2 is 100 to 400, and so on. Once you've defined these height classes, offline, you can figure out what portion of each GCM grid cell is within each height class. And then you stick these numbers into FHC and give it to ModelE, and that's all ModelE needs to know. So ModelE does not actually know the shape of these grid cells. It only knows that this grid cell is divided into 3. One has 20%, one has 40%, one has 20%. Okay?
But that's at some time. Obviously, that's going to change.
That's right. Well, we haven't gotten there yet in the code. So right now we're working on the one-way coupling and driving the ice sheet with ModelE. And so right now the focus is on generating surface mass balance fields. Once we start coupling it back, then that'll have to change. And I believe that this is related to a push to make more of the land surface types be able to change. Right, the height classes can change. Ice can change into land, bare ground. Bare ground can change into ice. Well, not in our climate. So those are not in ModelE yet. And then, yeah, this can also change. The mean elevation of each height classified cell, right? So this grid cell might have a mean elevation of 300 meters, whereas the different height classified portions of it, this one's 53, and that one's 125, and that one's 262, and so on. So we have to tell ModelE, we've created this new grid with a whole bunch more grid cells. We have to tell ModelE what's the elevation in each of them. Okay, so then what does ModelE do? It extends these prognostic land ice variables with this added dimension for height class. This ATM-GLA, which is used to transfer a lot of stuff between the atmosphere and the ground. Actually, ATM-GLA is atmosphere and land ice transfer variables. Well, now we have a whole array of them, one per height class, because we have to keep track of things differently. But we make sure that this one is always equal to the weighted sum of that one, weighted with those FHC numbers. Then we've added a height classified diagnostic category. It's called IJHC. So, I believe that land ice is getting height classified now, but other portions of the model, I've heard people might be interested in height classifying other portions later. So we have this nice general height classified diagnostics, kind of, so created kind of height classified versions. Created height classified versions of all of these AIJ diagnostics. So, there's still an AIJ as always, but now you can get per height class readouts on them in the IJHC variable. Okay? I see people are falling asleep. Okay, so then two other things have to change. Well, we change the variables inside ModelE. Well, we have to change what we give the input of ModelE. So the GISS file has been extended with height classes. Again, if NHC is 1, you won't notice the difference. So your old GISS files work, but if you want to run with height classes, you need to give initial conditions per height class. And also, if you're running with height classes, you need to use a netcdf topo file instead of the GISS format version. And it's double precision, and basically when you look into how you prepare stuff for ModelE and how you set up FHC, you have to change some of the things in the topo file to make the land portion percentages all consistent with each other. So I had to read in the old topo file, monkey with it a little bit, write out a new one. In the process, we changed it to double precision. So in the process, we changed it to netcdf. But again, your old topo files work if you're running with one height class.
Why do you need double precision?
Because just didn't want to be bothered with wondering whether I'm introducing errors by having these inconsistencies in my land surface types because they're only good to 8 digits.
Yeah, but it's much more than you usually able to measure anyway. It's just an input file.
Yeah, well now my land surface fractions add up to 1. So that's fine. Right, otherwise we're always going to be having to justify it and make sure that we haven't messed up our results and that kind of stuff.
Yeah, we ran into the same thing doing the land cover with single precision.
No, I mean it's you will never get exactly one.
Okay. Okay, so now we've monkeyed around with ModelE. We put in these height classes. We want to know a few things, and these are two separate questions. One is, how well can we represent real surface mass balance fields using this height classified grid? And the other is, how good surface mass balance fields can we create with our GCM? So I'm going to talk about the first one first. That's the easy question. So here it is. Here we have a real surface mass balance field. Well, actually, this is a real precipitation field. So this is from the RACMO Regional Climate Model, which is considered the gold standard for understanding Greenland's climate. So, no, we didn't actually have measurements every 5 kilometers all over Greenland, but somehow this is considered, the truth, unless someone wants to investigate and find otherwise. So then what we did was we upgraded this to our height classified GCM grid using area weighted remapping. That's like the HNTR regridding. And then I downgraded it back to the 5 kilometer ice grid. And I also used the smoothing algorithm that I developed this summer in the downgrading. And the neat thing about the smoothing algorithm, as opposed to say like bilinear interpolation, is that it gives you guaranteed conservation. So the total amount of precipitation in this picture is exactly the same. Actually, in all 3 pictures, the total amount of precipitation is exactly the same. To like 14 digits vectors.
I bet you 7 would have been fine.
Or maybe only 12 or 13 digits. So anyway, the idea is that we can generate surface mass balance fields on our height classified grid, and then we send them through our magic conservative smoother downgridder, and we get this nice smooth surface mass balance field that we can send into our ice grid. And in this case, you see that the precipitation field actually looks very close to the reality that happened on the 5 kilometer grid. So this gives credence to our idea that the original idea of height classes is that 2 portions of a grid cell that are at the same elevation should behave similarly. And this is showing that maybe there is something to that hypothesis. Maybe it's not just pure imagination. And so actually, I think if I got a surface mass balance field that looked like this out of ModelE, I'd be ecstatic. You see there are a few differences down here where there were these kind of localized effects of these bays or outlet glaciers or whatever that the height classification scheme didn't get. Okay, so the other question is, so right, it would be great if we can generate surface mass balance field to look like this in ModelE, but can we?
So the grid cell size in this experiment, is it comparable to what we have in GCM? Is it like cube sphere?
This is like,
Do you have like 1 by 1 or what?
let's see, 70, 75, so this is 2 degrees. So this is 2 degrees by 2.5 degrees right here.
Okay.
So yes, I haven't worked with cube sphere grids yet.
Mhm.
Certainly driving the GCM grid smaller should overall improve things, but it might introduce a few wrinkles as well. But, just haven't gotten there yet. I'm still working with obsolete GCM grids.
And here you're using 10 high classes.
Yeah.
Or more.
Yeah, the high classes were originally an idea at CESM, at NCAR, and they used 10 height classes that they defined. It was the same height class definitions in every grid cell. And so far, I've just taken what they used and used the same. Eventually, we want to figure out, well, can you get improvements by adjusting the height class definitions within each grid cell, and how much can you improve, and how do you best do that adjustment? But right now, we're just using constant height classes that are the same everywhere. Okay. Yeah. So the real question is, can we get fields that look like this? So kind of here's how it works, right? The GCM creates a temperature field, and this is only a portion of how it works. I mean, there are millions of variables, right? The GCM creates a temperature field on our GCM grid. It creates a precipitation field on the GCM grid. It creates an air pressure field on the GCM grid. Now we need to downscale all these things. We need to move them all to our subgrid tiles. So we need to. So let's start with precipitation, right? If we have a big grid cell, here's our big GCM grid cell, and say it's an average of 1,000 meters elevation, and I'm sorry, I'm dumb. What's the typical air pressure value at 1,000 meters?
900 millibars would be fine.
Okay, so we're at 900 millibars, right, for this cell. Now we chopped it up into 3 pieces, and this one has an average of 500 meters, and that one has an average of 1,500 meters. So now, you know, this one here needs to be more like what, 600 millibars?
Think of 1,000 feet, 1,000 meters at 100 millibars.
850.
850 millibars. Okay, and then so this one would be what, 1,100 millibars? Okay. And say this one, say that we just met, and say that then this main portion averaged out to 1,023 meters, and so that's 892 millibars. Okay. So there, we've just downscaled our pressure field. Nobody writes papers about this because, you know, it's pretty trivial. But it does happen, and you have to do it. Okay, so one down. The next thing is temperature. Now that's a little bit harder, right? So if we knew that it was, say 2 degrees Celsius here. Now we think that, you know, how do you figure out what the temperature? So the overall temperature is 2 degrees Celsius, and let's say that's close enough here. This is 2 degrees Celsius in the middle. Now going down to 500 meters. Well, what's the temperature, you know, down below where you really were? There are lots of ways you could do it. You could look up in the atmospheric column, maybe to get this. You could look at neighboring grid cells. There are lots of things we haven't tried yet. The simplest thing is you just, you know, hold your thumb to the wind and you say 5 degrees per kilometer. So now we know that over here, that's half a kilometer down, so we got to be 2.5 degrees warmer. So we're going to be 4.5 degrees Celsius there. And similarly up here, we'll be 2.5 degrees colder, so we're going to be negative 0.5 degrees Celsius. And so now that this is pretty cool here, because when we rain precipitation down here, you know, obviously whether precipitation comes down as rain or snow counts on a lot of factors and heat transfer through the atmosphere. But we all know, like, you know, we all know since we were a little kid that we can kind of expect it to be snowing here and raining there. Right? Right? It's 4.5 degrees there and it's negative 1/2 degrees there.
I don't even, if the water freezes at 0, but go ahead.
Well,
minus 38, yeah, for sure.
Well, you can give a talk about, you know, Einstein. Right. So ModelE can give us a better, you know, ModelE can give us a better estimate and understanding of exactly how the precipitation comes down, and it does do that. But the idea is we've now given ModelE different basic surface temperatures, and that will have a heavy influence. And this is really important because, right, we're trying to look at the surface mass balance of this ice sheet. It's really important for us to know whether it snows in a portion of the ice sheet and it stays there as snow and adds to the ice sheet, or whether it rains and runs right off. And especially on these grid, you know, in the ice sheet, right? All the action happens at the edges of the ice sheet. So, you know, that's where all the melting in Greenland is happening. That's where most of the precipitation is. And so it's really important to get this basic thing right. If you wanted to even have a chance of, you know, correctly modeling what's happening to these ice sheets.
It's more important that there's for the melting. Like Andy said, the precip probably doesn't change the phase of precip, but the melting. So if the
That's
surface is warmer than 0, it will melt, and where it's colder than 0, it will not melt.
That's right, right. Even if it falls as, you know, ice, it might melt, right? Yeah.
But really, in GCM, your precipitation is formed far above your surface. You actually have no information about your height classes inside the atmosphere. And you cannot change into snow because you have to put latent heat somewhere.
Yeah, so
it belongs somewhere.
Yeah, so we'll have to put the latent heat somewhere, and yeah, there's a lot
But
of
it
details
belongs
to work out.
up there where you have no control over.
Yeah, yeah. So I agree. I think there are plenty of ways we could get. I guess to me that's you know, yet another kind of unsolved problem that maybe we'll solve someday, is, you know, figuring out how to get that right. But certainly a prerequisite is to getting the temperature, the surface temperatures right, and that, you know, elevation has a big effect on that. So that's temperature. Now downscaling our precipitation. Okay, so air pressure was easy, right? Temperature is a little bit harder. Now precipitation is so hard that it's really scary. So we're going to look at.
That's what
We're going to look at, you know, the ice sheet from the side, and it looks kind of like that, right? And so, you know, here's our grid cell. You know, this whole, from here to here is one grid cell. And so now, you know, we think, you know, depending on the direction of the winds, which of course is complicated, but assume right now the wind is coming in here. You know, we think this is going to go up. A lot of stuff is going to fall down right here, and we're going to get less precipitation up there. And since it's falling at such low elevation, most of it will be rain. Meanwhile, ModelE is telling us that it's kind of more diffuse precipitation over this entire region because it has the orography all wrong. So people have developed these kinds of models to correct this. Forrested and Smith at Yale University. Ron Smith published a number of articles of increasing complexity on how to deal with this. And we won't need the really complex ones because they're for like mountainous regions. And here we just have a simple slope. But the stuff is out there. But then the problem is how do we take this precipitation that in one sense the GCM thinks should be over here and move it over to that grid cell instead? And you know, how do we do it in physically realistic ways that aren't parameterized?
Well, there's another issue, which is that in Antarctica you have a strong circumpolar component to the wind. I mean, you have the westerlies, and those are basically going up over ranges and down. You know, basically all the channels through which the ice is coming. So you've got leeward sides and windward sides.
Yeah.
And so elevation, there may not be a simple relationship between, you know, rainfall and elevation, just because it may depend whether you're on the leeward side of the mountain or the windward side.
Yeah. So within one grid cell, right? So yeah, that's okay. We've defined that relationship between elevation and temperature, right? Now we certainly, when you start getting into mountainous regions, you're going to need something. Yeah, the whole height class thing breaks down a little bit. You might need to do some things on the full ice grid to figure out where that precipitation is falling. So again, Ron Smith has papers that show you how to compute that and how to, you know, very complex mountain ranges. But yeah, that'll be a challenge.
Well, at the end of the day, what people are trying not to do is run a high-resolution regional model to figure out where the precip is, and so you're trying to guess what the answer would be if you did. So that's what's so hard about it.
You know, my approach going into this as well, those look like pretty hard problems, but at least that's, you know, we can't even, you know, we can only think about them in theory until we actually have a simple model running with the simple algorithms to benchmark against. So at this point, in my mind at least, it's all just guesswork of what's needed and, you know, not needed and how complex we have to go and what will work. Okay, so yeah, so right now we're not downscaling the precipitation. So kind of these things. Okay, so these variables, ignore this line of arrows. Kind of everything should point to everything else, right? So basically, we compute, these things like accumulation and runoff and evaporation and anything else relevant. We add them all up together, we get a surface mass balance on our height classified grid. And what does that look like? Hot off the presses, using a 5 degree per kilometer lapse rate, this is what it looks like. And so here you can see, right here you're going upslope, and as you can see, this is temperature, so our temperature gets colder, and the temperature also gets colder, say if you're going north, or depending on the weather patterns. This is averaged over 5 years. This is the average temperature in Greenland over 1950 to 1955. And here you can see that it's nice and toasty down at the low elevations, and it's really, really cold up in the middle. So I think that.
So here you're using this algorithm of 5 degrees per kilometer.
Yeah. Yeah, I tried everything from 0 to 9.
But I thought that you would, in GCM, you would use PBL actually to compute real surface temperature.
I don't understand how that works, actually.
Well, at the top of PBL you have atmospheric boundary condition for the entire cell. And you have PBL columns for each of your height classes. So that's what you were doing? No? Is it?
That's what I did.
Yeah, but or is it not used yet?
Downscaling of temperature on the previous chart was for downscaling of the first layer temperature that is used as the boundary condition.
Yes, I will say Max has done a huge amount of work to make this happen.
You're welcome.
Yeah, Max rewrote a lot of the code and added, height classified PBL and did a lot of things so that we could have what I just showed you before with these height classified variables. But once all that's done, there's the part where basically you stick in this 5 degrees kilometer or whatever your downscaling algorithm is. So last night, yesterday I tried a bunch of factors, and if it's too high, if your lapse rate is too high, what will happen? See, your temperature is going to go up as you move upslope, and then it'll go back down here when you get into the next grid cell, and then it'll start going up again. So you get these completely unphysical cross sections. So this was a little bit of a fudge experimental thing of try a bunch of things and see what kind of looks the best. And I thought that 5 or 6 looked the best. I think 5 looked the best. Now that's actually in line with, you talk to the glaciologists and they'll tell you, well, when you move upslope on a mountain, the lapse rate will be anywhere from 4 to 6 degrees per kilometer, which is different from the lapse rate if you move up in the atmosphere. So when I eyeballed it and got 5, that's within the ballpark. So there it is. So there's our surface mass balance field, and we'd really like it to be smoother because this isn't on the 5 kilometer grid. So we have the smoothing algorithm that can go from this one to that one, and we tried it a bunch this summer. We'll certainly want to try it on these real GCM outputs that we're getting. Haven't done that yet. So we could finish up a little bit early. I guess we have some time. We can talk about how the regridding works. Okay, so regridding. So the whole idea of the regridding now is to go from this kind of a field on the high classified grid to this field on the ice grid. to make it smooth and to do that in a conservative way. I'm going to talk a little bit about how that works. So if you want to, suppose we have two grids. Say here's this blue grid, and that's like the GCM grid, and we have this red grid, and that's like the ice grid. And I'm going to make an overlap matrix, which is defined as Lij is the area of overlap between blue grid cell I and red grid cell J. And if there's nothing there, that means 0. You see we get this kind of sparse matrix. And so you can define these in terms of polygons very exactly, right? If you don't know where your grids are, you're hopeless. There's nothing to be done. So you know where the bound, we know the exact shape of all our grid cells, and using enough computational geometry, we can create all these polygons inside the computer and run algorithms to find these overlaps and generate these overlap matrices. So, so I have these programs that generates overlap matrices, and it'll really work for any grids we like. It'll work for cubed sphere, it'll work for Lablon, any whatever. I'm not going to go into too much detail. Just know that it's general, that we don't have to think too hard. Now the other problem, of course, is that we're talking about, in our case, we're talking about the overlap between the GCM grid, which is on a sphere, and this ice grid, which is on a plane, because ice models think the Earth is flat. So actually, we have to, what I'm doing is I'm projecting the GCM grid also onto the plane, and then we compute the overlap. And there's this great theorem, I guess, or principle of cartography, that if you use an equal area projection, then the area of your grid cells doesn't change when you project them from the sphere onto the plane. And so therefore, you can actually compute the area of the overlap computation won't change either. So for, people like to plot their stuff in lots of different projections, but for use with ice models inside ModelE, I want an equal area projection. Whatever projection we use to compare the ice grid to the GCM grid, it should be an equal area projection. If it's not, you start getting these correction factors you have to be putting into your surface mass balance that have nothing to do with reality. They have to do with the fact that your grid cell just changed size when you projected it. And then those correction factors have to go in and they affect the physics. So, yeah. Okay, so once you have this overlap matrix, the next cool thing is that you can do like HNTR style, like it's called HNTR regridding, it's called area rate weighted remapping. All it is a matrix multiplying. Getting the overlap matrix is the hard part. Now you multiply by your overlap matrix and you divide by a factor, and boom, there you've got, there you've regridded your data. So right, if I can compute this overlap matrix for any kind of grid, on a sphere and any kind of grid or irregular mesh on the plane, now I can do simple area weighted rewrapping just, trivially. So that's pretty cool. But none of that's really new, right? People have known how to regrid for a long time. Now QP regridding is quadratic programming. So the thing is, what do we want? There are two things we want. We want our field to be smooth, and we want the total amount of mass to be the same. So what I mean, right, is this field here should be smooth, and the total amount of mass in this field, the sum of this field, should equal the sum of the field we started with. But I think we want something a little bit more than just conservation, right? We could take all the mass from here and put it right down here in the southern tip of Greenland. And as long as, I don't think you'd be too happy with that. So what we want is that within certain regions, we're going to define certain regions we call conservation regions. Say within each of those, the mass has to be conserved. So it kind of has to be conserved locally as well as globally. And right now, in this case, the conservation regions are the same as the actual GCM grid cells. So that's what we want. Right? We want it to be smooth. Well, how is it going to be smooth? Let's just minimize like the square of the gradient. So in kind of numerical terms, right? If you have an ice grid right here, and here's x sub ij, then you want to minimize like xij minus xij plus 1 plus xij minus xij minus 1. Right? So for every grid cell, you kind of look at its neighbors and you want to just minimize the difference between the two. So that's all we're really doing here. So we've put together, you know, a big function of all our xij's on our ice grid, and we want to, so we have like a million different numbers we're trying to compute in our ice grid, and we want that field to be as smooth as possible, and this is our definition of smoothness. And we also want it to be conservative, right? So that means, again, that, right, if here's x1, x2, x3, x4, x5, x6, right? We want x1, x2, we want the sum of these x's to be equal to what they started with. So that's basically this conservation constraint. So we've described the problem we want, and the cool thing is, you know, we've described what we want here. We want it to be conservative, and we want it to be smooth. And the cool thing is that's actually a quadratic program. So we don't have to think really much past that. You know, once we've written out as our, you know, the variables we're trying to constrain and get smoothness on, we just plug it. You know, this problem I've sketched out here is basically something that conforms to this kind of mathematical form, and so then we just have to solve the quadratic program, and you know, people have committed their entire careers to solving quadratic programs. So we use that, and then with that, so that's how we go from this picture to that picture. We just declare that I want it smooth and I want it conservative. We throw those declarations into a QP solver, a sparse QP solver, and it comes up with this picture. So now we're going to be wanting to do that with actual surface mass balance fields. So this is temperature, it's not surface mass balance yet. So we're trying to get the temperature as physically realistic as possible and the surface mass balance as physically realistic as possible before we go through that smoothing process. Because the smoothing process, you know, has really no basis in physics. But ice models certainly do like smooth inputs. Okay, so yeah, a lot of hard problems remain. We'll probably have to downscale precipitation. We need a handle on outlet glaciers, basal topography, roughness, ice shells. There's a lot of grunt work involved here still, you know, coupling these things back and forth, making land surface types change in ModelE. But that's basically where we're headed. Thanks.
When will you have a working ice model?
There are about 5 working ice models.
But no, for us.
I don't know. By the next grant deadline, right?
Does our current ocean model, is it raise or lower? Is it fixed?
No, no one has done the work to allow the ocean area.
So how expensive your smoothing algorithm is? You
Very
basically-
cheap.
Huh?
It's very cheap.
Really?
Takes like half a second
Half a second for what?
for those pictures I showed. Yeah. And
Yeah,
remember,
but you should think in terms of GCM algorithms. Usually you don't want to use Poisson solver or anything like that. Well, I mean,
It's
you
not
do,
going
but-
to be done every GCM time step.
yeah, we do
So
it once a month.
So it will be just for. Oh, okay.
So what's the resolution? What you call high and medium, and so the low resolution of the GCM, okay, but what are the other resolutions? In fact,
Okay, so the high resolution, that's the ice grids, and don't go to an ice conference today with a grid of larger than 5 kilometers.
okay.
And unless it's adaptive and you're like you can have large grid cells in the middle of ice of Antarctica, but you really need to be at 5 kilometer resolution or better where it counts. And people are talking about resolutions down to 1 kilometer.
So at your monthly time step, are you using the instantaneous precipitation on other things, or are you using?
No, you integrate it
you
over the
integrate?
month.
That makes more sense for mass balance. Yeah.
No, actually, there's something I glossed over that the ice models, all the ice models, because of the way the ice equations work. Right, here's our ice sheet, and they want to be told every time step. They want to be told 2 things. So say for this portion of the ice sheet, it wants. Okay, so it has grid cells. So in every grid cell, it wants to know what was the temperature for the last time step, and what was the mass added or taken away. And one ice model, the PISM model, works in enthalpy instead, so it talks about heat instead of temperature. But the problem with this is that we all know that there's no constant temperature over a month. And so the way ice modeling has been done so far is you kind of stick your finger in the wind, get a good average over the month, and you put that into your ice model. Of course, for two-way coupling, how do you do that in a conservative way? Well, you can't just measure the average temperature and then throw that to your ice model for the month. There will be no conservation of energy, which would get ModelE upset. So what we do is we need another model on top of our ice sheet, and this is the snow fern model. And it needs to be 15 meters thick. So, from an ice dynamics perspective, it's nothing. It's even thinner than the ice sheet. So you have this kind of 15 meters of snow or fern or whatever you call it on top. And we know that these daily and monthly and yearly variations, it acts like a capacitor. So you're putting heat into the ice, taking heat out of the ice. Every day you're doing that. And you're doing it with the seasons, but at 15 meters depth in an ice sheet, it's pretty much constant temperature. So we need to have our snow fern model talk with the atmosphere, and then it also talks with the ice model.
So it talks in the atmosphere every GCM time step, it talks with the ice model every month.
Yeah. So the snow fern model, right? So if the atmosphere dumps a lot of snow on it, now your snow's getting thicker. So instead of 15 meters, now it's 15.3 meters. So at the end of the month, it gives that 0.3 meters now. It gets rid of it and gives it to the ice sheet. So what snow fern model do we have? Well, currently our ice model, we actually have that right now. The current ice model in ModelE was from 1983. It has 2 layers. It has a top layer that's 10 centimeters. It has a next layer that's 2.9 meters. So it's really not thick enough, but it's what we have right now for free in the code. The plan is to replace that with the Stieglitz ice model, which is being used on regular land surface, right? We don't want one set of physics for snow and ice, you know, for shallow snow and ice on land, and then a completely different set of physics on our glaciers, you know, our ice sheets. So we're going to use the Stieglitz snow model that's already in ModelE and replace this with that one. And then we might have to beef it up somewhat to get these kind of 15-meter requests.